Our second speaker is Dr. Nick Brown from EPCC at the University of Edinburgh. Nick is part of the XACC program and also hosts his own computer acceleration testbed at EPCC as part of the UK Excalibur Exascale research program. And Nick is going to talk about his work on Lucent, a language for developing application-specific data flow machines.
Perfect. Thank you very much and good afternoon. I would say from sunny Edinburgh, but unfortunately it's getting dark here at the moment. So yes, I'm going to be talking about some of the work we've been doing on data flow programming languages. And I don't think anybody would argue with the title of this slide in terms of whilst Vitis makes the physical act of writing data flow code, HPC data flow codes, much easier physically for the FPGA, when it comes to getting that great performance, we still need to rethink our algorithms from the data flow perspective. And this can require quite a lot of expertise and time in order to do this. And I suppose, very generally speaking, there's two schools of thought about how we might go about fixing this. And the first one is on the left, where we say, look, let's stick with C, C++, the Pythons, and we'll get the compiler to detect all that data flow parallelism and do all the clever bits around the data flow side of things. And there's intermediate representations like MLIR, like DACE-IR that we've heard about in a previous talk, like Scale HLS, again, we heard about on a previous talk, that are very much in that space. The other end of the extreme is to say, no, it's the job of the programmer. They should be the one who are writing their abstractions in a data flow style, and the compiler's not going to do work trying to extract that. It will just do what it's been told. And I guess there's things like Maxilla's Java compiler that provide these abstractions and expect the programmer to program them in that way. And we're very much on this right side of things, really thinking what a correct language is, what the correct abstractions in order to enable us to give this capability to the programmer. Because if you're writing your code in C or C++ with HLS, obviously your execution model of the code coming very much from the von Neumann side of things is a million miles away from actually how it's executing on the FPGA. You know, you're probably thinking about this flow chart, about storing data with variables, and obviously on the FPGA, it's spread out across the logic. And this is a real pain with these two different views of things. And I would even go further than this and say quite a few of the pragmas and the concepts in HLS, things like pipelining, partitioning, dependence pragma, from the perspective of a programming language designer, they are required because of limitations in the abstraction. And if we had richer abstraction, then the compiler could guarantee these things and potentially make the job of the programmer easier in terms of getting good performance. So we decided to do some blue sky research, really going back to basics, thinking what's the correct execution model to give to the programmer so they can write fast by construction codes for FPGAs, and also as well to experiment with using Vitis HLS as a target language for higher level languages to translate or transpile into. And for this, we went back 30 or 40 years to when the computing community was looking at general purpose data flow architectures. The reason for that is, again, many of you will be very familiar with this. If I'm using HLS with the data flow pragma, with HLS streams, well, that feels very much like a data flow machine. But crucially, it's not a general purpose one. Instead, it's a data flow machine that I am developing that's utterly bespoke to my specific application. And I'll reconfigure the FPGA to look like it, and then I'll configure it to look like something else. So it made a lot of sense for this to be the abstraction, the execution model to give to the programmer, that of data flow machines. And then the next question was, okay, that's fine. But back in the day, how are they proposing actually programming these general purpose data flow architectures? And arguably one of the most sort of common things was this programming language called Lucid, developed by Bill Wadge in the 1970s. And it's a declarative language where one states the desired outcome of their task, but not focusing on the exact control logic or how it's achieved. That's the job of the compiler. And really the big innovation that Bill and his team made was to make the progression of time a first-class concern. And really, I think, to be honest, what they did was a bit too early for the time. You know, they did a simulator that ran on the CPU, but they never actually ultimately managed to run it on a general purpose Dataflow machine, unfortunately. I think the excuse was it was the wrong type of Dataflow that was provided by these machines when they finally came around in the 1990s. But some derivatives were developed in the 90s for FPGAs, but focused very much at developing circuits and real-time computation rather than our interest, which is an HPC software developer working top-down. Let me accelerate my HPC code, my HPC kernel on these FPGAs. But we thought this would be a great starting point. And really to develop a Dataflow domain-specific language that we called Lucent, that's based on Lucid. And what we're doing here, the proposition is subtly different. With our Lucent programming language, we want to empower programmers to develop their own application-specific Dataflow machines that then configure the FPGA. Whereas with Lucid, they were looking at programming existing general purpose architectures. But starting with this, they've done a load of good stuff, but still, it was fairly old-fashioned, very much a product of 40 years ago, and having to think about how to then bring this over to the Alveos and what programmers of the 2020s expect. Now, I don't want to go through all the different bits and pieces of the language because that would get very boring and there'd be no point. But instead, what I want to do is use some code examples really to highlight some of the key aspects, some of the key decisions we've made before I show you some of the performance numbers we've got and how this compares with other approaches for programming FPGAs. So at this code example at the top left, we've got this thing we call a filter. We mark it external, so it's visible to the host. It's typed to be an integer. And then we've got this line here, and this is declarative. So I'm declaring the outcome of this filter, which the stream is 12. And we have the progression of time as a first class concern. So this is 12 infinitely. For the first time, what we call quanta, the second time quanta, the third time quanta, the fourth time quanta, etc. And then we can add to this. So we can do more interesting things. For instance, here, we've got two input streams, and we are adding them together and streaming out the results like so. And then we've got this end of data token. It comes from Lucid. And when this gets streamed in, it just terminates it. And this is the view of our Dataflow machine. And down here, again, it's a little bit more advanced where we've got these internal filters. They're connected together, all running concurrently across the FPGA, connected by these calling them. But the idea is, from the perspective of the programmer, you don't care how these are implemented. You don't care how these streamers are implemented. It's just all running concurrently from one time quanta to the next. Now, based on those sort of very simple things, just to give you an idea on the other side of the coin, in terms of the compilation, we have our Lucent code, we run it through our compiler, and then it generates all the files needed to then run this just through the Vitis toolchain. So we've got the smarts, if you like, the device code over here, that's going to be then compiled for the FPGA. We've also got a lot of the underlying code needed for the host, and then it's fairly simple just to write some driver code like this. But then purposefully with this make file, we've tried to keep it as close to what Xilinx have in their tutorials, with things like make device, target for hardware, hardware emulation, software emulation, just so it seems fairly standard after you've run that through our Lucent compiler. And then you can run it in emulation or run it on the FPGA. We've also got this dot file that's output, and that's the graph viz view of our Dataflow machine. So here we've got these two inputs. They're always read in 512 bits for performance, and then they're unpacked into the integers. This does the business, and then we output it and again write it in 512 bits. But the programmer doesn't care. They just care about their logic, their declaration actually running. If we go a bit further on the Dataflow side of things, I suppose the big smarts is in this followed by operator. And this comes from Lucid. It's one of their major contributions. And this is a key part of how we control these different time quanta, because we're declaring that the value of this sequence here is 0 at the first time quanta, followed by every subsequent time quanta, A+1. So it's a counter incrementing the value. But crucially, we're very abstract here. And the reason that's important is for an integer, it's nice and easy. It runs on the Alveos in a cycle. But if this was floating point, well, this addition will take 7 or 8 cycles. And if we're not careful, we'll need to wait that number of cycles before we can do the next addition, and that will stall our execution. The compiler will see that, it will realize that's potential, and depending on how it's used, it will implement it a different way to keep the data flowing that's abstracted from the programmer. We've also got conditionals. So as we're streaming data through, at each time quanta, checking the value of the streams, and then doing different bits and pieces based on that, and then with these filters down here. And we follow similar sort of rules to HLS's data flow in terms of we don't allow circular dependencies. The output of one filter can't be fed back around as an input. And also, whilst our filters can have any number of input streams that go into them, based on Lucid, we can only produce one output stream. That's a limitation from the semantics of the language provided, I say, back in the day. Now, I've gone through that reasonably quickly, and it's fairly basic, but actually I was quite surprised. Based on this, we can do a whole load of stuff. And most importantly, in their book that they wrote about Lucid, they had a whole bunch of additional data flow operators that they'd hard-coded into their language. And we realized that actually, you know what? Based on these fundamentals, we simply don't need to do that. We can build all of these out of those basic building blocks and provide them in the language itself, keeping that core compiler, that core language, as simple as possible. And actually what we do is we provide these in a core module that gets imported and the programmer just uses them. And the reason I mention this is in some of the subsequent examples, you'll see this increment call. It's just a very simple count, but we just have it for convenience. Now, one of the key design decisions was whether we went with an implicitly typed language like Lucid was, or like things like Python, or whether we went with explicit typing, where the programmer has to set the types, everything in their code. And from this code example, you can see that we've got this explicit typing where we're saying everything is explicitly typed. And we thought that would be really quite beneficial because then we could exploit this further. And I've got an example of this where I've got my external filter with my types, but you can see I'm also giving it attributes to control those types. So for the external filter, I'm saying, look, we've got storage here in DRAM. So as I'm streaming out this data, it's getting stored in the DRAM on the board. And here, storage is in high bandwidth memory. Similar to type defs in C, we can have type variables. So here we've got fixed point precision that we've set, and then we're using it throughout the code. And again, it's just nice and convenient to have these single points of truth where we can easily play around with them. And we've got a whole bunch of different rules converting between double, single, half precision floating point and fixed point in terms of losing precision and warning the user. But also we can use the type system to get around one of the big limitations of the original Lucid. And that is that filters can only stream out one stream. And we tried to fix this in a variety of ways. It was really nasty from a language perspective. And then we realized actually we don't need to, because we can make a multi-stream a type, a bit like a struct in C. So still, the compiler sees this as a single stream, but the type is multi-stream that combines multiple streams internally combined together. And we can access these by index and also by name as well. Now, the last thing to say on this before talking about some performance is we've also got lists, so multi-dimensional lists. Again, we're at this high level of abstraction, so often the compiler can look at how we're using this from the perspective of the code and pick out issues such as exhausting these dual memory ports on the list in terms of the number of concurrent accesses. So I can then just partition this up to keep the data flowing. And for instance, here, this is a one-dimensional shift buffer. It uses sort of Lisp-style operators to take the tail of the list, so the last elements ignoring the head, and then concatenate this with the input. Each cycle, each time quanta, so effectively, this is shifting through the data and streamed out. We can also control where lists are stored, and list is also how we do vectorization. So here, for instance, we've got an input of these streams of lists, we output a list, and in this one operation concurrently, we're performing 8 double precision multiplications together. So based on that, we then did some performance comparisons with BLAS operations. And I wrote really quite quick and dirty versions in our Lucent approach. I've got a sketch of the dot product at the bottom here. When you know the language, it's quite quick and easy to write those. And then I also developed a quick and dirty version in C++ with HLS, not looking at doing any optimization, but just enough to get it working. And so you can see the comparison here between running in Lucent and running just native HLS without any optimization. And without any exceptions, we're quite a bit faster, in many cases a lot faster. I then took the Vitis BLAS library and did a comparison against that. And with the Vitis BLAS library, you can control how much parallelism it's got, how many elements it's processing per cycle effectively. So this here is no parallelism, just one element per cycle. I'm actually quite surprised that it wasn't that much faster than my naive implementation, if I'm honest, and our Lucent approach is quicker. But the maximum amount of parallelism I could get it, and the furthest I could push it in terms of the performance, was to 16 operations per cycle, and all that concurrency is what's making this way faster here, which is really nice from the perspective of the BLAS library. And you can see, we don't have any concurrency here with the current version, so this is winning out here compared with this. So the next version around here is to then use some of these list vectorization to make these more complicated, to then see how far we can push this based upon that parallelization approach. Now, this was all good, but what we realized, actually what the Lucid team realized about 30 years ago, is there was a big limitation. And that is, we're viewing the progression of time as constant and the same rate for all parts of our algorithm. And actually, that's quite limiting, because often you want to pause a stream and keep using a certain value time and time and time again, and then go on to the next one. Or alternatively, you want to iterate some filter internally time and time again, build up some internal state, and then simply throw it away and then start all over again. And in the original Lucid, they developed a whole load of constructs to sort of do this. But then in the 90s, they realized they could replace all of them with this concept of time dimensions. But they never actually got around to implementing this. And we hit the same issue, but then realized we had to implement it in our model. And to give you a view of this, what we've got here is what we've talked about up until this approach, where we're simply counting up to 10 and feeding 10 into this identity filter, sends it straight back. Here it's different, because what we're saying is in each of these identity filters, it's its own sub-time dimension. So from the perspective of the higher level default time dimension, calling this is an atomic time quanta. It's an atomic step. But in here, there might be lots and lots and lots and lots of sub-time quanta, lots and lots of sub-steps going on. And it might be consuming this lots of times over, but it's the same value that's sent in here, and it will only produce one value out because it's one atomic time quanta. So I can maybe give you a slightly better view with this simple code to calculate which prime number from the first 20 integers is prime. And for each number we're testing with this simple implementation, we've then got this is prime filter that we're going round and round and round again, building up some state in order to return true or false if it's not prime. So this is run in a time dimension for each number, where we send the number in, and then it does lots and lots and lots and lots of runs with that number, and then sends out true or false. And from this perspective, it just sees it as one atomic step, consuming one value here and returning one value out. And what's quite nice is we can provide this replica to here, and it will just, the compiler will produce multiple copies of this and run them concurrently and give us a whole load of guarantees around the order of bringing data in and sending data out. And a slightly more advanced thing here is a 2D Jacobi example. So thinking a bit more from the perspective of HPC, solving Laplace's equation for diffusion, where we're doing 10,000 iterations. And what we want from the perspective of the default time dimension is for each iteration to be one atomic step. So it's doing all of these over the stream within this sub-time dimension. And what you can see here is we've got the shift buffer. This is a 2D shift buffer. We just provide it in this buffer package that's, again, written in Lucent that we provide as part of the language. similar to our 1D one, but slightly more complex because it's 2D. What's a bit nasty here is you can see we've got this stream size and this magic value. And that's because from one iteration to the next of this time dimension, we need to buffer the data. And we use a ping pong buffer. So we're writing data out into a buffer, and then we're feeding it back around as an input. And we need to store that and know how big that needs to be. So this is a bit nasty. I think we can tighten this up, but it's also why these domain sizes are quite small here, because we wanted to have plenty of VRAM with this. I think we can make this much better by giving an option to the programmer to store this in high bandwidth memory external to the chip. So therefore, take this performance comparison with a bit of a grain of salt, because the domain size is very small, but you can see we're not a million miles away from the fastest that we could run this on a Cascade Lake on the CPU with OpenMP, but certainly some optimization still to do in our compiler, and bigger problem sizes will give us a bit more information here, better comparisons. In terms of performance comparisons, just a couple to very briefly mention here. We went with the advection kernel of the high resolution atmospheric model from the Met Office. So this is the model they use for quite a small area, but at very, very high resolution meter scale, looking at how the atmosphere progresses. And the movement of particles through the air is about 40% of the runtime. In previous work, we ported this manually into HLS and compared it against the CPU. And that was about 600 lines of code. It took us quite a long time to implement efficiently. In Lucent, it's 23 lines. So it's much, much smaller, much quicker to program once you know the language. And yes, it's a little bit slower than hand coding this currently, but not massively slower. And again, I think there's some tweaking we can do at the compiler level, exactly what we're generating to tighten this up. Now, an important thing here is we're only using a fraction of the FPGA. So even though we are slightly short of the 24-core CPU, actually with this one, we can scale up to 6 kernels. And we could do the similar here. We just haven't yet because we're focusing very much at the individual kernel level and getting that data flow fast by construction. And then lastly, just the other example is a credit default swap engine. This is simulating what we call the spread. It's an insurance policy for the non-payment of loans, basically. So you give it lots of data and lots of options, and then it will simulate the progression and give you the spread, which is the amount you should be charging for the insurance policy. In previous work, we did a hand-coded version of this, and we compared it against Xilinx's Vitis implementation, their quantitative finance library, and against one core of the CPU. Our implementation was over 700 lines. Again, it was a bit of a pain to get working and get working fast. 73 lines in Lucent, so it's much, much smaller. And again, it's a bit slower in terms of options per second. Higher is better, but it's not a million miles off. And again, I think we can tighten this up and bring the performance closer in. And we're beating pretty convincingly the Xilinx version, which is more optimized for flexibility and ease of integration. Again, in that further work, we scaled up the number of kernels, and that was then competitive with the entire CPU. And that would be the next step after we close down on the handcrafted version in Lucent. Now, just wanted to finish about some comments about HLSC++ as a target for compiling into from higher level languages, because absolutely it's got all the functionality there and you can absolutely do this, but you do need to play around with it quite a bit. Different constructs for loops, for instance, we found will give you quite different performance in terms of the initiation interval. So we spent lots of time generating code in the HLS GUI, looking at the scheduling viewer, and then figuring out what works and feeding it back. Also, software emulation works completely differently to hardware emulation and the hardware itself. So again, having to play with getting that working. But the biggest headache is quite simply, we're not using HLS in the way that Xilinx intend. And so we write out this end of data from some parts, it gets progressed through, it shuts things down, but we then need to get that back up to the preceding parts. And we can't send it back up directly in the kernel. So it's really nasty. What we have to do is fire that on out to another IP block, which will pick it up. We'll send it back right to the start of our filters, feed it all the way down, and make sure everything is shut down. So we have to do these workarounds to get this working exactly as we want. But as I say, it's really, I suppose, our fault for using this in a way that Xilinx haven't really intended. And we see this with these time dimensions as well, and these nested data flow regions, and some of the challenges in terms of deadlocking and consumption of data, again, can take us some time to get that working. And thankfully for hardware emulation, because it's obviously much quicker building than the hardware itself. So just to conclude, our focus is very much on this sort of high level, giving the language and the abstractions to the programmer. And I think we can write fast by construction code using these sort of approaches. And it's quite interesting to look back at what was developed previously and see what we can bring to the modern world. Of course, it's not realistic to expect programmers to learn a new language or new paradigm, but this is a sterile environment to explore these different abstractions. And as part of Excalibur, we've got a project looking at domain-specific languages and bringing some of these onto the FPGA. And I think this gives us a nice comparison point. So going forwards, we're looking very much at getting access to the Versals and seeing if we can apply this to AI engines, because I think they're going to be very interesting to program manually. And I think, again, maybe we can do some interesting things there from this higher level view of the user's code. So thanks very much for listening. And if anybody's got any questions, please ask.
That was great, Nick. Thanks very much. I think you preempted my question with your last slide there on the Versal AI engines. I'll go straight. We just have a couple of minutes in the session left. I'll go straight to a question in the Q&A. Can you talk about how you've implemented Lucid? Are you using something like Xilinx Alveo and as a source-to-source compiler to HLS?
So yeah, we do a source-to-source compiler from Lucent into HLCS Plus. We're not using Clang or anything. Actually, what we're doing is we're using Bison and YAC, and then just a bespoke compiler written in C++. Maybe that sounds quite overhead, but my background is compiler, so I've got a lot of the tool bits and pieces, so it's quite easy to bring them together and pull these things in. Currently, it is C++ HLS. Obviously, Xilinx have opened up the front end, so we could come in at the LLVM IR level as well, but it's just really useful to be able to have the C view and experiment with that human readable code. So that's why we've kept at that level currently.
Okay, and one more question. This may be future work. Are there any MOOCs, massive online courses on Dataflow programming with Lucent?
Not yet. It's still very much work in progress. I mean, I've talked about tuning and tweaking these different things. But yeah, it's still very much work in progress to make sure that it's going to fully support all the programs people want to use. The problem with these things, the problem with programming languages and compilers, is somebody comes along with a program you'd never even thought of, and it's got to work for that. So we think this is interesting, and we've started to put a bit more engineering around this, but it is now moving up the technology readiness level to make it more available. So we do have some documentation, some examples and tutorials, but I think there's quite a bit more we need to do to make this more accessible and consumable.
Just one last question that's come in. Does Lucent allow programmers to use CAPI?
So there's no reason it couldn't. Currently, we go out into, we're focusing very much on Vitis and the Alveos, but it is just HLS code fundamentally. Yeah. So we think absolutely things like CAPI and maybe something like an alpha data card, for instance, with a Kintex on it, absolutely we could do that, no problem. We might need to do a little bit more, slightly different things on the hosts, but there's no reason fundamentally why it couldn't, absolutely. Yeah.
Thank you to both our speakers today for two great talks. A reminder that you're welcome to apply to join our XACC program to get access to those high-end Alveo compute acceleration cards that have been referenced in the talks, and also to join that community of researchers. You can find details on the webpage shown. You can also find recordings shortly of this talk and previous tech talks if you would like to watch again or share with your colleagues. The first part of today's session from Chris mentioned Elastic DF. We actually had a tech talk on Elastic DF last June if you'd like to go back and watch that one and find out more about Finn and the work that was done there.